third experiment in the handbook. And the last experiment is determination of the internal resistance of a cell using the potentiometer. And this is my this is the 34th experiment in the book. Right, so all of these experiments are listed, are explained in the following order. So first I introduce the equipment and then go over the theory behind the experiment, then setting up the experiment and collecting data, and finally calculation, conclusion, and discussion. So all of these experiments are done according to these 4 steps. Okay, so let's go over the first experiment, that is the determination of the internal resistance of the electromotive force of a dry cell. So if you carefully read this title of this experiment, you may find 2 new terms, the internal resistance and the electromotive force. So what are those terms? Let's try to identify those terms first. The electromotive force, which is EMF, the phrase electromotive force actually has nothing to do with the force. It's just the potential difference in volts. Okay, so the electromotive force or EMF of a battery or cell is the maximum possible voltage that the battery can provide out of its terminal. So actually, does the battery provide the maximum voltage? No. Why? Because battery has the internal resistance. So we know that the batteries are made of matter. Thus, there is a resistance to flow the charged particles within the battery. So this resistance is called the internal resistance. Okay. So what we are going to do in this experiment is to find out an internal resistance of the electromotive force of a dry cell. Okay, so let's quickly go over the list of equipment. So I'm not going to read these and just have a look, and then next I'm going to show you a video that's explain all these instruments. Okay. So while you're reading, I'm going to play my first video. Okay. So I hope you can all can see the video. So I pause for a while. So that's what you see. That's the dry cell you see on the screen. So the cell or the battery has polarities. So the little bump you see on the top is the positive side, the plus sign, and the bottom side is the negative side of the battery. So let me play this video. That's the positive side, and the other side is a negative. So here you see the milliammeter, the instrument we use to measure the current. So you can see little m and capital A. So the little represent the milli, 10 to the -3, the A represent ampere. So this instrument is used to measure current in milliampere range. Okay? So this instrument has polarities, plus minus. This is the connector used for the plus side, and this connector is in black, that's for the negative connector. So when you connect this instrument in a circuit, we need to make sure that this has to be connected in series connection. Okay, let me pause, play this video. So that's the positive side, and that's the positive side. The other side is a negative. Yeah, this is a voltmeter. We use this instrument to measure the voltage of the circuit. So we connect this instrument parallelly to the circuit, and in fact, this is this is an analog voltmeter, and this voltmeter has plus and minus connectors, the polarities. So the red connector is the plus side, and the black connector is the negative side. So that's the plus side. That's the negative side of the voltmeter. So this is called the rheostat, a variable resistor. The rheostat has no any polarities. Let me wait for a little while. So, okay, here. So here you can see the connectors of the rheostat. Let me pause this video for a while. So these are the three connectors of the rheostat. You have one in the top and the two on the sides. So when you connect the rheostat to the circuit, so we have to connect one of the wires to the top connector, and the other one should go in one of these connectors. The rheostat, as I mentioned earlier, the rheostat has no any polarities, no plus and minus. So we can connect the rheostat to any side of the circuit. Okay, so let's suppose the positive wire is connected to this connector, and the negative wire of the circuit is connected to this part. So how does the current go? So the current flow through the positive wire, go through this rod and go to the bottom and go through this part, and then leave through the negative wire. So this part is this length is the effective length for the resistance. So you can move this black knob here and there. So as you move it, you can change the effective length of the resistance. So we can get the different resistance values. So that's called a tap key. This is very similar to the push button. This is like a switch also. So when you press that part, you can close the switch. So you can see the connectors. What you here you see is we need to, when you press the key, we need to press firmly, and those are the two connectors. So the connecting wires should go into those connectors, and we need to press firmly in order to make the connection between the two wires. And these are the connecting wires. And the last component is the resistor. In fact, this is a 10 ohm resistor. The resistor has no polarity, so we can connect the resistor to any side of the circuit. So, and the resistor has two ends. Those are the two ends of the resistor. All right. So let me close this. Right. So we went over this. All right. So let's try to understand the circuit diagram, and then we can see the setting up the circuit. So here, the battery, the dry cell. The dry cell is connected to the voltmeters. What we are going to do here is to find out the voltage, the terminal voltage of the dry cell. So the dry cell is connected to the voltmeter. So this is the positive side of the dry cell, and it is connected to the positive end of the voltmeter. And the negative side of the dry cell is connected to the negative side of the voltmeter. So the voltmeter is connected parallelly to the dry cell. Okay, so the dry cell can be modeled like this. So I mentioned that the cell has an internal resistance. So this resistor connected in series to the dry cell is the internal resistor. Okay, so the E represents the maximum voltage that the battery can provide. In other words, the EMF, electromotive force. Okay, right. So this is the voltmeter, and here's the milliammeter connected in series. So the negative end of the milliammeter connected to the negative side of the dry cell, and the positive end is connected to the tap key. And here's the 10 ohm resistor to limit the current flowing in the circuit, and this is the rheostat or variable resistance. Okay, so let's see the experiment setting up these components in the circuit. So I'm going to share you the video. In the meantime, I will show you the method of doing this experiment, then I'll show you the video. All right, so here's the battery holder for the dry cells. So this wire is connected to the positive end of the battery, the holder, and this wire is connected to the negative end of the holder. Okay? So we use the brown color, red color for the positive ends of wires, and the black or blues for the ground or the negative sides. Okay, let me clear this. So that's the dry cell. Here's another dry cell connected in series. So here, these, okay, let me pause. Right, so these two ends are connected together inside the holder. So these two batteries are connected in series. So that's the voltmeter. So the positive wire of the the dry cell is connected to the positive side of the voltmeter, that is in the red color. So that wire has to go to the negative side of the voltmeter, since the voltmeter is connected in series, parallel. So that's the ammeter to measure the current in the circuit. So as you see in the video, he connected the negative side of the voltmeter to the negative side of the ammeter. So the positive side is connected to the tap key. So the other end of the tap key is connected to the 10 ohm resistor. So that's the variable resistor or the rheostat. So the other end of the resistor, one of the ends of the resistor is connected to the rheostat. The top connector of the rheostat, and so we can use one of those connectors of the rheostat. And that goes back to the voltmeter or the positive side of the cell. That's complete the circuit. And we need to make sure that they connect the negative end of the cell to the voltmeter negative connection or the ammeter negative connection, because these two are connected together. That's the voltmeter reading. If you have good eyes, you can see the needle of the voltmeter. It's just past the 3 volt value. And here, once you press the tap key, the needle of the ammeter is deflected. You can see, and we can get the different current value by changing the rheostat knob, the resistance of the rheostat. So he increased the resistance. So now he decreased the resistance. We should expect a higher current value. So what we are going to do here is we record the voltage and the current flowing in the circuit by pressing the tap key. and we change the resistance of the rheostat, and then record the current value and the corresponding voltage value. So now you change the rheostat, the resistance of the circuit, and record the voltmeter value, and press the tab key and get the current value. Okay, so let's move to my slides. Okay, so you can see the circuit diagram on the left side of the screen, and here at the right side you can see the equations. So the V is the terminal voltage. That's the voltage of the drive cell, terminal voltage of the drive cell. So that is equal to the voltmeter reading. Okay, and the terminal voltage is equal to E minus IR. So what is E? E is the maximum possible voltage coming out from the battery. Okay, in other words, that's the EMF, electromotive force. Okay, and then this is the potential drop in the internal resistance. So there's a potential drop. So that's why we put a negative sign here. Okay, so the internal resistance controls the flow of current or charge particle. So there's a potential drop. So that's why we have the negative sign. So the potential drop in the internal resistance is equal to the product of current and the resistance according to Ohm's law, I times R. Okay, so if you rearrange these terms, I can get the negative IR plus E. And what we did in this experiment is we changed the resistance value and record the current value to that resistance, and also we record the voltage value. So the current is changed according to the resistance you set in the circuit. So that's the independent variable. So the voltage is changed according to that current. So that's the dependent variables. So if you plot the current values you collected in the experiment on the x-axis and the voltage values on the y-axis, we can get y equals mx plus b graph. Okay, so the slope of the graph is corresponding to the internal resistance of the drive cell, and the y-intercept is the EMF or electromotive force of the drive cell. Okay, so the next slide you can see the graph. Okay, so that's my mouse. Yeah. So the graph, so the voltage in volts, the current in amperes. So here's the graph, then you get the negative slope, and the slope is corresponding to the internal resistance, and the y-intercept, this point is the EMF. So these are the sample data set we collected during the experiment, voltage and the current. In milliamperes, the voltage in volts. And here's the plot. And these are the data points. And this is the best fit line. And this equation represents the slope and the intercept, y-intercept. So my conclusion is the gradient of the graph is negative 0.959 ohms. So the internal resistance of the cell is 0.959 ohms. So the intercept of the graph is 2.851 watts, and so the EMF of the cell is 2.851 watts. Okay. So let's do the discussion. So here I have a couple of questions. My first question is, why do we start the experiment with the largest possible value with the rheostat? Okay. So it's because we need to make sure that there is a small current flow through the circuit at the beginning. So you know that there's a ammeter connected to that, so we need to protect the ammeter. So we usually don't start with the high current, since there's an ammeter, it has a very low internal resistance. So we typically start with a small current flowing circuit, so that's protect the ammeter also. Okay. And why do we use the 10 ohm resistor? That is also the same purpose. So that is to limit the maximum current flow in the circuit. And my next question is, what properties you must have in a voltmeter and ammeter, and how do you connect them in a circuit? So the voltmeter is used to measure the potential difference between 2 points in a circuit, and it has to be connected in parallel to the points. By connecting the voltmeter, we should not interfere the circuit function, so it must have very large resistance. In ideal condition, it should have an infinite resistance. So, so we use the analog voltmeter. If you use the digital voltmeter, the voltmeter has very high internal resistance, typically in mega ohm range. And so the current flow through the voltmeter is very, very small, negligible, almost zero. An ammeter is used to measure the current in a circuit, and it is connected in series in the circuit. And in this case, the ammeter must have very low resistance and ideally zero resistance. But in fact, the ammeter has very, very small resistance. If you use the high resistance, you cannot get the accurate current measurement. So the resistance of the ammeter is very, very small. And my next question is, what is the purpose of using the tap key, and how do you use it properly? So the answer is, by using a tap key, you can let the current flow in the circuit for a short period of time. This is an advantage since the battery will not get discharged quickly. However, when you use the tap key and when you press the tap key, in order to have the connection, you need to make sure that you press it properly so that the connector touches very well. So what's the advantage of using digital voltmeter? So that's to get the higher accuracy value. So digital voltmeter, as I mentioned, has a very high internal resistance in mega ohm range. So if you use a digital voltmeter, so it has a higher, we can get a more accurate data. Why do we have to draw a graph and do our findings? Why we cannot do single measurement and find the values? So I hope you know this answer for this question. So we take the multiple readings to increase the accuracy of our results. Okay, so let's jump into my next experiment. That's the determination of temperature coefficient of resistance of a metal using the meter bridge. So we use the copper as a metal for this experiment. So this is the list of equipment. Okay. So I'm not reading this list. So just have a quick look. And then my next video, you can see and hear the description of these instruments. Okay. So let me. Okay. So now I'm going to show you my next video. Just hold on 1 second. I need to share the. Let me play this. Wires to the end of these two. I think the previous portion of the video, you didn't hear the sound, so let me play that again. We used to find out the temperature coefficient of the copper. So the 40 SWG stands for standard wire gauge. Is 40, so it's around 0.12 millimeter diameter wire. So this is a center zero galvanometer. As you see on the screen, the zero is at the center of the scale, and there's an indicator to find out the current flowing in the meter. So it's very useful to find out the current direction in the circuit. So if we get the positive current, so the indicator will move to the right side, whereas if we get the negative current, the indicator moves to the left side of the scale. Okay. And there are connectors to the 3 connectors to the galvanometer. So when we you set up the instruments, a circuit, I will explain how to connect the galvanometer in the circuit. So these are called the plug keys. It's the typical function as like the switch. So we can connect the wires to the end of these 2 spots, and there's a plug in the middle. By taking off that plug, we can disconnect and connect. In other words, we can close or open the switch. So this is a thermometer that we use to measure the temperature of the water. So this thermometer has 0 to 100 centigrade scale. So we can measure up to 100 centigrade temperature. Yeah. So you can see a Bunsen burner and a tripod and a beaker filled with water, and the middle of the beaker and the tripod has a wire mesh. Okay, so we place the beaker on the wire mesh, and we submerge the copper wire inside the in the water to get the temperature coefficient. So this is a 5 kilo ohm resistor. As I explained in my previous experiment, the resistor has no polarity, so there's no plus or minus, so we can connect the resistor to any ends of the circuit. So this is called the variable resistor box. So there are 2 ends. There are 2 ends in black and red. The black typically stand for the ground wire connector, but there is no polarity as I explained earlier, so you can connect any ends, but typically the black for the ground or the negative, the red for the positive end. And you can also see the knobs. So by changing these knobs, we can set up proper resistance of get out the proper resistance from the box. So instead of taking a fixed resistor, we can get different resistance out of this box. So this is another instrument to get the variable resistance. By sliding on the top of that knob, you can get the several resistance. So this is called the rheostat or the variable resistor. That's the knob that's sliding. We connect the wires to these two knobs in black wire. So those are the ends to connect the wires. You can also connect the wires to the top of the knob also. These are the connecting wires that we use to connect the circuit. All right, so let's move on to our slides. All right. So this is the experimental setup. So now you know the instruments that we are going to use for this experiment. So here is the meter bridge. This part is the meter bridge. So this is the wire in the meter bridge. And this is the lead accumulator. You will see in the my next video, the lead accumulator. So the positive side of the lead accumulator is connected to a circuit, a switch, K1 switch, and this is connected to this side of the meter bridge. Okay, and the other side of the lead accumulator, negative side, is connected to the other end of the meter bridge through this rheostat. Okay. And here these are the strips, metal strips, and you can see these. There are two gaps. They are not connected to each other. Okay, and this is the Bunsen burner, the tripod, the wire mesh, the beaker, stirrer, thermometer, and this is the coil. Copper coil, and the two ends of the copper coil is connected to this gap. Okay, so the copper coil has resistance, so we include the resistance. We connect the resistance of the copper wire here, and the other gap of the meter bridge is connected to this resistance box. Okay, and this is the galvanometer, center zero galvanometer, and it is connected through a 5 kilo ohm resistor and a K2 switch. That is to protect the 5 kilo ohm is to protect the galvanometer. This is the switch, plug key, and the other end of the galvanometer is connected to this metal strip. Okay, right. So, so what we are going to do in this experiment is we are going to take the resistance value with respect to the temperature. So here we are going to find out the temperature coefficient, that is the alpha. So here in this experiment, in this equation, you can see the relationship between the theta and the resistance. Okay, so so the resistance is changed. So where's my mouse pointer? So resistance is changed according to the temperature, the value. Okay, so what is this alpha? This little fish, that's the alpha, that's the temperature coefficient. So what does the temperature coefficient tells us? The temperature coefficient is telling us how the resistance of the material is changed according to the temperature change. How is the variation of the resistance with respect to the variation of the temperatures? That's what the temperature coefficient is. Okay, so that's what we are going to find out in this experiment. So what we are going to do here is we change the temperature of the coil and find out the resistance according to the change of the temperature. Okay, So let's, so that those are the, this is the method of doing this experiment. So let me quickly go over the method. What we first do is we open the switch, both K1 and K2. So open the both plugs and then close this K1 switch. Okay, so then once you close the switch, the current start flowing. So since this path is open, this switch is open, this is disconnected. So the current flow through this 5 ohm resistor. Okay. So the 5 ohm resistor, it's not the 5 ohm, no, it's 5 kilo ohm resistor. So the 5 kilo ohm resistor actually protects the galvanometer. Okay. And then by changing the sliding key of the galvanometer, by sliding over this wire, so we can get the rough balance point first. And once you achieve the rough balance point, we put the plug back into the switch, and then the current flow through this switch, this path, so the less resistance path, and then we can get the more accurate balance point. So that's the brief method of doing this experiment. Okay. Right. So let's me show you the video of setting up the equipment and doing the collecting the data. So let me show you this. Yes, that's a plug key. So that's a meter bridge. So here what you see, that's the lead accumulator in blue. So the key is connected to the meter bridge. The switch is connected to the meter bridge. And the other end of the switch is connected to the lead accumulator. Okay. So that's the other end of the lead accumulator. So that goes to the rheostat. Okay. So current goes top of the rod of the rheostat and then go through the black part. So we use that the connector that she showed you to connect the other end of the meter bridge. Yeah, so that's the connecting the wire to the rheostat, and then so that wire is connected to the other end of the meter bridge. That's the resistance box. Yeah, so those are the two ends. So that goes to that part of the empty part of the meter bridge. So that's the switch, and the 5 kilo ohm resistor goes to the galvanometer. So the one end of the switch is connected to the meter bridge, the middle part of the meter bridge, and the other end is connected to the galvanometer. That's a center zero galvanometer. So that's connected to the switch and the 5 kilo ohm resistor. That's a sliding key. So there's another gap in the meter bridge. So we need to connect the coil to that gap. That's the wire mesh and the tripod. The Bunsen burner. That's the beaker with water. And you can also see the stirrer in the beaker. Yeah, I can see the thermometer inside the beaker too. So that's the copper wire, in fact, a coil. So that wires, the ends of the copper wire go to that the empty end of the meter bridge. So that's submerged in the water to get to heat up the coil. So when you turn on the burner, so make sure to stir the water to get the uniformly distribute the temperature, the heat in the water. So that's the first. We take off both plugs and then put only the K1 switch. That's a switch for the lead accumulator. That's the switch you have seen a moment ago. That's a sliding key. So when you place the sliding key at the ends of the meter bridge, the galvanometer shows you the deflections in opposite directions. So if you cannot find a good balance point, what we're going to do is we change the resistance of the resistance box and then get the balance point. So once you receive the rough balance point, we put that plug key of the switch connected to the galvanometer, so then we can get the more accurate balance point. All right. So let me slides. I hope you can see my slides. Right. Let's go to my previous slide. Okay. So what we did here is we increase the temperature of the copper wire. In other words, we heat up the copper wire, so the resistance is changed, and then we obtain the balance point. Okay, so what do you mean by the balance point? So how do you obtain the balance point? The balance point we obtain by using the center zero galvanometer. So at the balance point, the needle of the galvanometer has to be aligned to the 0 point of the scale. In other words, if the needle is aligned with the 0th point, that means there is no current flow in this part of the wire. In other words, there is no current flow in the galvanometer. Okay, if the needle is aligned with the 0. Okay, so what does this mean? If there no current means the potentials at the end of the wires are same. So that's why there is no current flow in this part. Okay, so the potential of this point is same as the potential of this point. Okay, if you take the other part of the resistor of the meter bridge, this part is directly connected to the this part of the meter bridge. So these two potentials are same. So at the balance point, the potential difference of this part is equal to the potential difference of this piece of the wire. Okay, so these two potentials are equal. So what is the potential difference of this piece? That is, if I current is flowing in this road, in this path, the potential difference is I times R theta. What is the potential difference or the voltage of this portion, this piece of the wire? That is equal to K times L1. What is the K? K is the potential gradient of the wire. Okay, so these two potentials are equal to each other at the balance point. So same argument goes to the other side of the meter bridge. So if once we obtain the balance point, these two potentials are equal together, and also these two potentials are equal together based on the connection. So the potential difference between these 2 points are equal to the potential difference between these 2 points of the wire. So the voltage means the potential difference. The voltage of this part is I times the same I, because it's same, the single path, the same I times RB, that's the voltage of this part portion. And what is the voltage of this piece of the wire? That is the K times 100 minus L1. So we can read the L value from here. So this portion is the 100 minus L1. So the K times 100 minus L1 is the voltage of this piece of the wire. All right. So these are the two equations I mentioned earlier. So if you divide these two equations together, so we can cancel off the current I from the left side of the equation, and the right side of the equation we can cancel off the K values. Okay, so we get this R theta over RB ratio on the left side of the equation, and the right side we have the L over 100 minus L. Okay, so now we need to introduce the alpha, the temperature coefficient. So how do you introduce alpha? We can replace the theta, the R theta, using this formula. So here R theta equals R naught times 1 plus alpha theta. And here the theta is the temperature, and the R theta is the resistance of the copper wire at theta temperature. And R naught is the resistance of the copper wire at 0 degrees centigrade. And alpha is the temperature coefficient. So we can rewrite R theta in terms of this product. Okay, R naught times 1 plus alpha theta. So, so in this line, that's what I have done. So instead of R theta, I wrote R naught times 1 plus alpha theta. Okay, and then we can rearrange this equation. So I have L over 100 minus L on the left side of the equation, and the right side of the equation, I have R naught times alpha over RB, and I take the theta outside the parentheses, and plus this ratio R naught over RB. So what we did here is we heat up the coil, and then measure the balance point corresponding to that temperature. So we have two sets of data. So one is the temperature values, and the other set is the balance point, the length values. So if you plot the temperature values on the x-axis, and this ratio, the length ratio, L over 100 minus L ratio on the y-axis, we can obtain y equals mx plus b type of graph. Okay, so the slope of the graph is equal to this ratio. So the numerator I have R naught alpha over RB. A numerator I have only R naught times alpha, and the denominator I have RB for the slope. And the y-intercept is equal to R naught over RB. So here's the graph, the sample graph. So we can have this type of graph. And the y-intercept is this ratio, the slope is this ratio. So to obtain the temperature coefficient, we can divide the gradient by the intercept. So the R naught over RB ratio will be cancelled off, and then we can isolate alpha. Okay. So the next slide, you can see the sample data we collected during the experiment. The first column is for the temperature in degrees centigrade, and the second column, the length in centimeters, the corresponding balance point for each temperature values. Okay. And the last column, the third column, is the ratio that we put on the y-axis. Okay. So here's the my plot. Remember this this ratio, the length over a length. So the numerator has centimeter unit, denominator has centimeter unit, centimeter cancel off. So this ratio has no unit, and the x-axis is in degree centigrade. So you can see the data points, and the blue line represent the best fit line. And here's the formula. So this is the formula for the best fit line. So this is the slope, and this is the y-intercept of the best fit line. So my conclusion is the temperature coefficient of a resistance is equal to gradient over the intercept, so which is 0.00397% degree centigrade. The actual value of the temperature coefficient of the resistance of the copper wire is 0.00386 degree centigrade. So we can find the percent error. So percent error is the difference between two values over the standard value. So this is the difference, the numerator, you have the difference, and that's the absolute value divided by the standard value times the 100%. So you can get the percent difference, 2.85% for this experiment. I think, so this is per degree centigrade. I think I mentioned in my video, it's centigrade, so it's a per degree centigrade. Right. The final part of this experiment, discussion. I have a couple of questions for the discussion. My first question is, when we are using the meter bridge in this experiment, why do we use 5 kilo ohm resistor? Can we use a smaller resistor than that? The answer is we are using 5 kilo ohm resistor just for the safety of the galvanometer. So it is always good to use a large resistor. For this purpose, as I mentioned, the galvanometer has a very, very low resistance, internal resistance. So if high current pass through the galvanometer, it's the fuse will be easily blown up. So we have to use, we need to make sure that it passes very, very small current through the galvanometer. My second question is, since we need to make sure, since we need to make measurements at a given temperature, how do we make sure that the copper wire is at the right temperature? That's a good question. So we usually heat the water beaker to a little bit higher than the temperature that we need, and we remove the burner and let it cool slowly. Then we can take the reading while the copper coil is reaching the required temperature slowly. So what does it mean? So that means, for instance, let's say you need to take the measurement at 32 degrees centigrade. So what we do here is we heat up the water up to 33 degrees centigrade and take off the Bunsen burner and let it cool. once the temperature is to 32 centigrade, we get the balance point. So that's how we collect the data during this experiment. The last two questions. How do we use the sliding key properly? So when we are using the sliding key, we need to make sure that we do not sweep out the wire with the sliding key. So we just have to touch and lift the sliding key up for the next position. The reason behind this tip is to make sure that the meter bridge wire is not get damaged. So we need to maintain the uniformity of the wire. So you know that the resistance is inversely proportional to the area. So if you damage the cross-sectional area of the wire, so if you damage the wire, the resistance of the wire will be changed. So we cannot get the accurate result. So we should not sweep out the wire with the sliding key. And the last question, so why do we use a water beaker to heat the wire rather than heating it straight away? So the answer is we need to make sure that the whole coil is in the same temperatures. Therefore, we heat the coil straight away. The coil may not reach the required temperature. So we use the water beaker to heat up the wire. All right. So I have two more experiments to do. So let's take a quick break, like maximum 3 to 4 minutes. And I will be handing the controller over to Mrs. Parker.
Register with Nexus Research Center, and it is guaranteed that you can learn the complete list of experiments and achieve success in chemistry, physics, and biology. How to register? Through the Google form link provided in the chat box. Once you get into the page, make sure you scroll down and click the next button.
Okay, so let's get back to our slides. Let me go over here. Right, I hope you can see my other slides. So this is my third experiment, the comparison of electromotive forces of two cells using the potentiometer. So this is the list of instruments we are using for this experiment. Just have a quick look, and then I will show you the video of introducing these instruments. So in this experiment, what we are going to I'm going to show you the video. So in this experiment, what we are going to do is to do comparison of electromotive forces of two cells using the potentiometer. Here's the potentiometer you see on the screen. It's very similar to the meter bridge, whereas this has 6 meter long alloy wire. You can also see the meter stick to measure the length of the balance point when we do the experiment. And this is the sliding key. It's very similar to the sliding key we use in the meter bridge to get the balance point. And you can see the connecting wire. So one of the end of the sliding key is connected to the potentiometer. So I will explain in details when we set up the experiment. So this is the empty Lagrange cell. So here we use an empty cell for demonstration purpose. What you see in white is the container made of plastic. And we filled ammonium chloride inside the plastic container, and that's on the others on the left side of the screen you can see the porous pot, and that is made of filled with carbon and manganese oxide mixture. So it's a sealed container, so we cannot open it and show you. But in the middle of the container has a carbon rod. That's what you see on the top of the pot. So that's one of the electrodes for the cell. And the rod that he's holding is made of zinc. So that's another electrode goes with this Lagrange cell. So when the solution is filled, that's how the porous pot is in the middle, and the zinc rod is in the ammonium chloride. So this is the second cell we use for this experiment. That's called the Daniel cell, and it is made of, the container is made of copper, and that's the porous pot. And the copper container is filled with copper sulfate solution. Yeah, we put the copper sulfate inside it. Okay, and the porous pot is filled with zinc sulfate solution. Okay, and the rod you see on the screen, that is made of zinc, so that goes into the porous pot. That's the inside the zinc sulfate solution. You can also see the. Can you put that again? So you can also see the connector on the container, copper container. That's the other connector we use to connect the cell to the circuit. So zinc connector and the copper connector. So these are called the electrodes. So this is the center zero galvanometer to measure the current flowing inside the circuit. So I explained the center zero galvanometer in my previous experiment, so I'm not going over this in details. So that's very useful instrument for this experiment. Okay, so this is called the plug keys. Actually, this is a two-way plug keys. It's very similar to the switch. Yeah, so it's very similar to the switch. When you take off that plug, we can disconnect the connection, and when you plug it back, so we can make the connection back. So it's very similar to the normal switch. Yeah, so these are the plug keys again, but this has only one switch, whereas the other one I showed you earlier has a two-way switch. So this is the 5 ohm resistor. We use this resistor to protect our galvanometer, and the resistor has any polarities, so you can connect the resistor to any ends, and those are the two connectors, two ends of the resistor, and these are the connecting wires used to set up the experiment. All right, so let's see my slide. This the material list. Okay, so here's the experimental setup. So this is the potentiometer, okay, the middle, and this is the lead accumulator. So you will see the lead accumulator in the next video. So this is the positive side of the lead accumulator, the plus side. So the plus side is connected to this end of the potentiometer. Okay, so the negative end of the lead accumulator is connected through the plug key or the switch to the other end of the potentiometer. Okay, and these are the two cells. So one of these will be a Lagrange, the other one will be the Daniell cells. Okay, so we use one cell at a time to take the measurement during during collecting the data. So let's say we use the top cell. So to select one cell at a time, we use this two-way switch here. So we can select one cell at a time. Okay, so this connection is very important. As you see in this circuit diagram, the positive side of the lead accumulator is connected to the left side of the potentiometer. So we need to make sure that the positive side of the Lagrange or the Daniell cell has to be connected to the same end of the potentiometer, which is the left side of the potentiometer. Okay, the negative end of these cells are connected to the galvanometer through this 5 kilo ohm resistor and the switch. Okay, and then here's the other end of the galvanometer connected to the sliding key. Okay, so I mentioned the purpose of using the 5 kilo ohm resistor to protect the galvanometer. So at the beginning, we open the switch, the K2 switch, so the current flow through the 5 kilo ohm resistor to the galvanometer, so we can obtain the rough balance point. Okay, once you get the rough balance point, we close the switch by putting the plug into the plug key. So then the current flow through this path, the low resistance path. So, and then we can obtain a more accurate balance point. Okay. So when we set up this circuit, before taking the data, the first thing we need to check whether the circuit is correct or not. Okay. So we, at the beginning, we take off both keys, K1 and K2, and then put the K1 back. So close the switch, K1 switch. So the current start flowing. So then we put the sliding key to the left side of the potentiometer near the A point and see the deflection. So suppose that the needle is deflected to the left side of the scale, okay? And take the sliding key and put it over the right side of the potentiometer near the B end. So that the needle has to be deflected to the other side of the scale. So we should have the opposite direction of deflection in the galvanometer. If not, our setup is wrong. Okay. So that's the first thing you need to do is check whether the setup is circuit is correct or not. Okay. Next, say how to set up this circuit and collect data. Okay, and I will show you the method. I'm not reading the method, but I will show you the video of setting up the instrument and collecting the data. Okay, so while you are reading, I will play my next video. All right, here's my next video. So that's the potentiometer. That's the two ends of the potentiometer. So that's the lead accumulator. The wire is connected to the one of the connectors of the lead accumulator. The other end of the wire is connected to the one end of the potentiometer. So that's the plug key, which is connected to the lead accumulator. So the other end of the accumulator is connected to the plug key. So the other end of the plug key is connected to the potentiometer. So that's a two-way switch, two-way plug key. So the center connector of the two-way switch is connected to the potentiometer. So that's the Lagrange cell. So the middle rod is the positive electrode. It's made of carbon, so that's the carbon rod that goes to the two-way switch. Okay, that's the Daniel cell. So that goes to the two-way switch, and please note that the copper, this electrode is the positive side of the Daniel cell. So that's the negative end of the Daniel cell, that which goes to the through the middle of the Daniel cell. So this is the negative end of the Daniel cell. That's a zinc rod. So the negative ends of both cells are connected together. Okay. So that goes to a plug key. So that's a 5 kilo ohm resistor to protect the galvanometer. So that's a 5 kilo ohm is connected parallelly to the plug key. Okay, so that end of the plug key is connected to the center zero galvanometer. So that's the sliding key. Goes to the galvanometer. Okay, so first we take off the keys of the switches and then put the plug back to the switch near the lead accumulator. So now we need to select which cell we are going to use. So now both are disconnected. So now, so here by putting that plug key back, then the lead launch cell is selected, the white cell. Okay, so we need to check the deflection of the galvanometer. So if you have good eyes, you can see the deflection of the needle of the galvanometer when he places the sliding key on the sides of the potentiometer. All right, so then we take a rough balance point So now the current flow through the 5 kilo ohm resistor. So once you obtain the rough balance point, put the plug back to the switch, and then we can get the accurate balance point. So the center, the needle of the galvanometer has to be aligned with the 0 value. So we can take down the balance point for the Leclanche cell, and now to get the measurement for the Daniell cell. So let's put the key first for the accumulator, and now select the Daniell cell. Now the Daniell cell is selected. And now it's checking again the deflection of the galvanometer, and now obtain the rough balance point for the Daniell cell. Once you obtain the rough balance point, take back the plug key back to the switch, and then we can get the accurate balance point. So that's the balance point for the Daniell cell. Okay. So now I'm going back to my slides. Okay. Let me show you my slide. Okay. So you know the method. So let me go to my here. Here's the circuit diagram again. So once we obtain the balance point, so that means there is no current flow through this part. Okay, so that's what the balance point means. The balance point means the needle of the galvanometer is aligned with the 0. So the current flow in the galvanometer is 0. What does it mean? That means the potential of this point is equal to the potential of this point. So these 2 points have the same potential. Okay. And how about this side? So potential of this point is same as the potential of this point. Okay. So suppose that the top cell is selected now. So the potential of the cell, the top cell of this point is same as the potential of this side. So therefore, the potential difference between these two cells, these two positions, are same for the potential difference of these 2 points. Okay, so potential difference means the voltage. So voltage of this piece of the potentiometer wire is same as the voltage or the EMF of the top cell. So EMF of the top cell is E1, and what is the voltage of this piece of the potentiometer? That is the K times L1. What is K? K is the gradient of the potentiometer, potential gradient. So we can write E1 is equal to the K times L1. So we can obtain the same type of relationship for the Daniell cell. So the E2, that's the EMF of the Daniell cell, is equal to the K times L2, a new balance point. So if you get the ratio, if you divide those equations together, so E1 over E2 is equal to L1 over L2. So K will be cancelled off. Okay. So these are the 2 measurements we took for this Leclanche and Daniell cell, and the ratio is 1.26. Okay. So the conclusion is the EMF of the Leclanche cell is about 1.26 times that of the Daniell cell. Okay, that's the very simple conclusion for this experiment. Okay, here's the discussion. Good question, the beginning. Explain the possible ways of introducing errors to the reading. What are the possible reasons for not having deflections in positive and negative direction of the galvanometer. Here I put you three reasons. The first is that instead of connecting the positive terminal of the cells E1 and E2 to the positive terminal of the potentiometer cell E0, their negative terminals may have been connected. I mentioned at the beginning of the experiment, when you're setting up this circuit, so make sure to connect the positive side of the lead accumulator to the positive side of each cell. Okay. If not, we do not get the deflection from the galvanometer. My second reason is there could be a loose connection in the potentiometer circuit. And the third is the potentiometer cell, which is E0, the lead accumulator, is discharged, hence has an electromotive force less than those of E1 and E2 cells. So the E0 cell has to have higher EMF compared to the voltage or EMF in E1 and E2. Here's another question. What possible things may have happened if you did not see a deflection in the galvanometer at all? If you do not see a deflection at all in the galvanometer, there could be two things can be happen. The first is there may be disconnection in the circuit, or the galvanometer may have been damaged. The last question for this experiment, can we do anything to increase the accuracy of our finding? Yes, we can. We can use the graphical method. That means that we can plot a graph. So for this purpose, we can use a resistance box connected in series to the potentiometer circuit and get the and change the resistance and get the corresponding balance point for each resistance. And then using the graphing method, we can obtain a very accurate, more accurate balance point, L1 and L2. Okay, so here's, I'm going to do my last experiment for today. Before I'm doing this, I just want to take a quick break. My director, Mrs. Paduka, was planning to make a couple of announcements during last break. Due to technical difficulties, we couldn't do that. So let's take a quick break, and during this break, you will hear a couple of announcements. So let's take a 1 to 2 minute break. So I'm handing the controller over to you, Mrs. Paduka.
With Nexip Practical Research Center, and it is guaranteed that you can learn the complete list of experiments and achieve success in chemistry, physics, and biology. How to register? Through the Google form link provided in the chat box. Once you get into the page, make sure you scroll down and click the next button. Register with Nexip Practical Research Center, and it is guaranteed that you can learn the complete list of experiments and achieve success in chemistry, physics, and biology. How to register? Through the Google form link provided in the chat box. Once you get into the page, make sure you scroll down and click the next button.
Okay. Yeah, so let's thank you, Mrs. Paduka. So let me take over right now. So let's jump into my last experiment. That's finding the internal resistance of a cell using the potentiometer. That's the 34th experiment in the physics handbook. Okay. So this is the list of equipment for this experiment. So here's our last experiment. So I'm going to show you the video corresponding for this instrument. So here's our last experiment for today. So what we are going to do in this experiment is to find out the internal resistance of a cell. Here we use the potentiometer as in the previous experiment. So you know the potentiometer right now. So let's move to the other instrument. That's the sliding key. Yeah, here you can see the sliding key. So these are the dry cells to use for the experiment. So that's the resistance box, variable resistor box. So we can change these knobs to get the different resistances out of this resistor box. So that's the tap key. The functionality is very similar to the push button. So as long as you tap the key, the switch makes the connection, and when you take off your hand, it's disconnect from the connection. So that's the tap key. It's very similar to the push button. So this is the center zero galvanometer. And finally, these are the connecting wires. All right. Let's go to here. Okay. So the final circuit diagram. This potentiometer on the middle, and this is the lead accumulator. You will see in a minute. And the positive side of the lead accumulator is connected to the left side of the potentiometer, and the negative side of the accumulator is connected through this switch, the plug key, to the right side of the potentiometer. Okay, and here's the dry cell. The internal resistance is represented by little r. The positive end of the dry cell is connected to the left side of the potentiometer. So you can see the positive side of the lead accumulator and the positive side of the dry cell, both are connected to the same side of the potentiometer. So that's very important. Okay. And here's the resistance box connected parallelly to the dry cell. So here we use another plug key, and the other end of the dry cell and the resistance box is connected to the galvanometer through the 5 kilo ohm and K3 switch. Okay, so you know the purpose of using the 5 kilo ohm here, and then here's the sliding key connected to the galvanometer. Okay. Yeah, so when you take the measurements, the first thing we need to do is to check whether our circuit is correct or not. So how do we do that? So we place the sliding key near the left end of the potentiometer or near the A, and see the deflection, and then move back to the other end, the right side of the potentiometer, and see the deflection. So that these two deflections should be in the opposite direction or in the galvanometer. If not, the circuit is wrong. Okay, so that's the first check we do before taking the data. Okay, so here's the method for collecting the data. So I will show you my last video for today of setting up this experiment and collecting the data. Ah, let me, let's play this. So this is the potentiometer. That's the lead accumulator. That's the potentiometer. That's the lead accumulator. The switch, the plug key connected to the accumulator. So the accumulator is connected to the one end of the potentiometer. So the other end of the accumulator is connected to the switch or plug key. So we open the switch first. Since we connected the lead accumulator, so it's a best batteries. First we open the switch and connecting the rest of the instrument to the circuit. Yeah, so that wire is going to the other end of the potentiometer. That's the resistance box. So by changing those resistance, by changing those knobs, we can get the different resistance out of this box. That's the dry cell. But we are going to find out the internal resistance of the dry cell. That's the tap key. So the resistance box is connected to the tap key. So we press the tap key during the data collection. That's the dry cell. So we connect the dry cell parallel to the resistance box. So that's a parallel connection. So that's another plug key for the galvanometer. So that plug key is connected to the tap key. So that's the 5 kilo ohm resistor used to protect the galvanometer. So the plug key and the 5 kilo ohm resistor are connected in parallel. So here he made a connection between the tap key and the plug key, and also the 5 kilo ohm resistor. So that's a center zero galvanometer. So we can use either connectors. So let's use the negatives, and the negative end is connected to the sliding key, and the positive, the center connector, is connected to the 5 kilo ohm resistor. Okay, so as you can see, the switch is open. So when you connect the circuit, the current is flowing through the 5 kilo ohm resistor and through the galvanometer. Now the circuit is not completed, so we need to connect the other side of the circuit. The dry cell is not connected to the resistance box. Now he's connecting the dry cell to the resistance box. So what he showed earlier was we need to match the positive side of the dry cell to the positive side of the potentiometer, the accumulator. So now the circuit is completed. Now we are ready to take the measurement. So but the first we need to check the deflection of the galvanometer. So both switches are open. So now we put the plug back to the key, the switch, and that switch is open. So the current flow through the 5 kilo ohm resistor. And here's the sliding key. So place the sliding key near the ends of the potentiometer and see the deflection. So if the deflection is in the opposite direction, then the circuit is correct. Now he's taking the rough balance point. Okay, so press the sliding tab key and get the rough balance point. And once you obtain the rough balance point, we can get the more accurate balance point, placing the key back to the plug key. So here we set the resistance starting with 50 ohms and then get the balance point, and then we reduce the resistance to 45 by 5 ohms at and then get the balance point. So likewise we reduce the resistance by 5 ohms at a time and get the balance point. So he's recording the resistance value and the balance point, the corresponding balance point. All right, so let's move to my slides. Okay. Right, so here's my circuit diagram. So once we get the balance point, no current flow through this part. So the potential at this point is same as the potential of this point. So once we reach to the balance point, there is no current flow through this part. That means the current current of this circuit, this little square, the current flow inside this little square. Okay. At the same time, the potential of this end is same as the potential of this end of the wire, and the potential of this end is same as the potential of this end of the wire. So the potential difference of this piece of the wire, that is the voltage of this piece of the wire, is same as the terminal voltage of the battery of these two ends. Furthermore, since the resistance box is connected parallel to the dry cell, the voltage across the resistance box is same as the voltage across the dry cell and the voltage across the this piece of wire. Okay, what is the voltage across this piece? That's the K times L1. K is the potential gradient. And this is the terminal voltage of the dry cell. And here the voltage is I times R. I is the current flow in this circuit, this little square, this little circuit. Okay, so that's what you see in this slide. These are the three voltage equations. So here's the voltage, the terminal voltage across the dry cell, E minus IR. E is the EMF, the maximum possible voltage coming from the possible voltage between the two terminals of the battery. Okay, and this is the voltage drop according to the in the resistance, internal resistance, I times R. So that's the voltage across the dry cell. And this is the voltage of the potentiometer wire, K times L. And this is the voltage across the resistance box, I times R. Okay, these are the three voltages. So we can equal, so first I equal the first two voltages together. KL equals E over, so instead of I can write V over R ratio. And now I replace V, the voltage, with KL product. So here, okay. So, and then I divided every term by E times L. Okay, so if you divide this term by E times L, the L cancel off, K over L, I get K over E. And the right side, E is cancelled off. Here I get L cancel off, and K over E times the resistance, the internal resistance, times the resistance of the resistance box. Okay, so if you rearrange these terms such that the 1 over L goes to the left side, and the other terms goes to the right side. So I can rearrange as K times R over E times 1 over the resistance box, resistor, and plus K over E ratio. So what we did in this experiment is we changed the resistance of the resistor box. That means we changed the R value. So that's the independent variable. So we have set of data for the R values, and we measured the corresponding balance point, the L values. So we have set of data for this L. So we can find out the 1 over L ratio also. So if you put the data values you obtain for 1 over R on the x-axis and 1 over L on the y-axis, we can obtain y equals mx plus b type graph. So the slope of the graph is equal to the KR over E ratio, and the y-intercept is equal to the K over E. Okay. So here's the graph, 1 over L versus 1 over R. So we can have this type of the slope. So the slope or the gradient is K times R over E. The intercept is K over E. To find out the internal resistance, we can get the ratio between the gradient and the intercept. So the gradient over intercept, so the K over E will be cancelled off, and we can isolate the internal resistance R. So here are my sample data. For the first column, the resistance value, actually we started with the 50 ohm resistor, and then we reduced the resistance by 5 ohm at a time and get the corresponding balance point. Okay. So the balance point is in centimeters, resistance is in ohms, the SI unit for the resistance, and centimeter is not the SI unit. So I convert the centimeters into meters on the last column and get the 1 over L ratio, 1 over L inverse of the balance point. And this is 1 over R per ohm values. Okay, so we can plot these data points versus this data point. So that's my graph. 1 over L goes to y-axis, 1 over R goes to x-axis. The data points are shown in black color, and the best fit line is in the blue color. Here's the formula. So 0.267 is the slope, and 0.3 is the y-intercept of this specific line. Okay, so my conclusion is the internal resistance of the cell is equal to 0.89 ohms. So I don't have a discussion for this experiment. The discussion is very similar to the discussion we had in the previous experiment. I hope you have learned something out of these experiments, and what you have learned today will help you to achieve good grades on incoming exams. And I would like to take this opportunity to thank Nexit Research Center providing this type of free webinars to give some like a better understanding of the experiments that we do in our A-level curriculum. I wish you all the best and thank you. And I'm giving the controller over to Mrs. Padukka, take the rest of this program.
Thank you, Doctor, for your valuable time. Thank you, attendees, for joining us. Hope this was of much use to all of you. Register with Nexit Practical Research Center, and it is guaranteed that you can learn the complete list of experiments and achieve success in chemistry, physics, and biology. How to register? Through the Google form link provided in the chat box. Once you get into the page, make sure you scroll down and click the next button. You can also follow up at your Facebook page, Nexit Practical Research Center. Thank you once again. Thank you all for joining us.